Hello and welcome. What we have here are two examples to illustrate the difference between a regular annuity and an annuity due. And we're going to do that through two examples. The first one is example 5.22. We have Andrea Mullins. She has just won the lottery in the US and it pays $50,000 a year for 20 years. So again, recognizing that this is an equal payment for a specified amount of time, qualifying us for the definition of annuity for educational purposes. She is to receive her first payment a year from now. The lottery advertises this as the $1 million lottery because $50,000 times 20 equals $1 million. If the interest rate is 8%, what is the true value of this prize? So what we would need to do is to calculate the present value of this annuity. We have the formula for the PV of the annuity here, and as a method number one approach to solving this, let's actually just use this annuity formula here. So we have C equals, that's the cash flow, so 50,000. And then we have two arguments that are going to need to go inside of a bracket, 1 divided by R, that's going to be equal to 1 divided by, R is 8%. And we have 1 divided by, I'll just do first the denominator here, R times 1 plus R to the power of T. So equals 0.08 times 1 plus 0.08 to the power of T here, which is 20. And I believe that's right. And I have an order of operations error. I'm assuming that's going to actually fix it. What I can do now while I'm here is just put that all in brackets, and I'll do 1 divided by, and cut and paste that here. So this is 1 divided by R, 1 plus R to the power of T. Not very fun to watch. So now this is just a simple matter of us putting this together into the formula to calculate the PV. So here I have the C, and I'm going to multiply that by this, subtract this. And I get 490, 907, which I think is correct. All right. So this is one way of going about it with a formula like this. I'll call this like method 1. However, I'm generally not a big fan of relying on formulas, really maybe just as a method to just check your work if you're using other methods. Maybe just as a method to check your work, because in problems like this, there's always more than one approach. So you can use this as one method, and if the answer matches another method, likely you've got it correct. My favorite method is to put this as a timeline. So here I'm going to have time, and I'm going to go from 0 all the way to, how many years do I need? 20 years. So I'm going to just copy paste this and go all the way over till about 20. Maybe I'll bold and center this. So I have time here. I'm going to need to know the cash flow associated with this. So 50 years, a year for 20 years, she receives her first payment 1 year from now. So she's going to receive a $50,000 payment 1 year from now. Time period 0 is always right now. And then time period 1 would be 1 year from now. The discount rate is 8%. And what I'm going to do is calculate the PV of the cash flow. And this is just the simple formula, present value of a single amount. So I'm going to take my future value, which is the $50,000 in 1 year from now, divided by 1 plus the discount rate to the power of n, which is 1. So the present value of $50,000 in 1 year from now is, if 8% is a true discount rate, is this 46,296. So now I can just copy and paste this across all 20 years, and I get the present value of a single amount basically 20 times. And now to calculate the total PV associated with this annuity, I'm just going to sum together those 20 individual amounts. And I get the same number, 490, 907, 37. So that's method number 2. So maybe I'll just put this all around in a border. Method 3, and I know I have to insert some rows here. My apologies about that. Would be using either your financial calculator or your built-in time value of money functions in Excel. And let's just assume that we don't know anything other than we need to calculate the present value of something. So presumably you know how to insert a function, and you know the PV function exists, and you can see that all I need is rate and per payment for this to work. So I'm just going to type rate and per payment, and we're going to be calculating PV based on those arguments. So this is our third method here. My rate gives us 8%, and per, I think it was 20, and we get $50,000 per period. So equals PV. Rate and per payment. Present value is this 490,907. So this is 3 different methods, and I can see that I get the same amount with all 3. So presumably, like I haven't made an error 3 separate times. So I have a consistent response in all 3. Now that's the ordinary annuity. Let's compare and contrast this to an annuity due, where we have the payment that is made at the beginning of the period. And I like to do this back to back because it really illustrates the impact of discounting. So for example, so let's just read the problem here. In example 522, we're now on example 527. Andrea received $50,000 a year for 20 years as a prize in the U.S. lottery. In that example, she was to receive the first payment a year from the winning date. Let us now assume the first payment occurs immediately, but the total number of payments remains at 20. So I'm actually going to just copy and paste my response from earlier, especially this timeline response, because I want to illustrate this. So if I just copy paste, it shows that the answer is the same. But I haven't edited this whatsoever. If the first payment occurs at the beginning, that means the first payment occurs right now at time period equals 0. So what I need to do is copy paste this over 1, because the first payment occurs now, because it's occurring right now. That means that it's actually not being discounted at all. But the total number of period payments remains at 20. If I just added a new payment into this timeline, that means there's now 21 payments in total, because I haven't deleted the one at the end. So I have to delete this 20th payment, so that there's or the payment in time period 20. The 20th payment would be 19, because the first payment occurs in time period 0. You can see here now that I get a slightly different answer. Because this first payment really is not being discounted at all. So because of that, it's actually much higher. So here, to compare the first one, where it's the ordinary annuity, there is no payment in time period 0, but there is a payment in time period 20. The payment in time period 20, the present value of which is basically only $10,000. Here, with the annuity due, there is no payment in time period 20, but there is a payment in time period 0. So we're basically swapping out a PV of 10,000 for a PV of 50,000. But because of that, what we can do to roughly get from this answer to this answer is just get our original answer times 1.08, and we'll get we'll get approximately the exact same answer. Why? Well, because here we're basically not at all discounting this first payment. Okay, but let's replicate this with Excel. It won't exactly work copy paste with what we've done. If I double click on my formula, you can see I have the arguments I need, rate and per payment. However, these other two arguments, f, v, and type, they're in square brackets to indicate that they are optional arguments, meaning that by default, they will work if you don't include them. By default, the future value is going to be 0. If it's not going to be 0, you need to put it in. And the type, by default, is always at the end of the period. But what we can do is just add those in. So I'll say FV and type here. And I'm going to put 0 as the FV. So let's just delete this and equals PV. I have rate and per payment. My future value is 0, and I have type as 1 at the beginning or 0 at the end. So I'm going to put here type, and I can just change this from a 0 to a 1. 0, 1. And there we have it. I hope that you found this useful. If you have any questions, please feel free to reach out. But we have here a compare and contrast of an annuity versus an annuity due, recognizing that the annuity due should always be higher because the first payment is not being discounted. All right. Thank you very much. Take care.